Two truths and a lie, but with math. Can you spot the fake? First, the best way to pack circles into a square is unknown except for one specific case. When there is a perfect square amount of circles, this type of configuration is the most optimal. As for the other way around, which is packing squares into circles, we are so clueless that we haven't even solved the problem for 3 squares. Last fact, a cube can be cut into 27 smaller cubes using 6 cuts. 2 here, and 2 more here. You might try to be more efficient with your cuts by rearranging the pieces of the cube after each cut, but it turns out you still need 6 cuts no matter how much you rearrange stuff. Here are all 3 facts, time to lock in your guess. The third fact is true, and there's a clever reason why. Look at the small cube in the very center. It's connected to 6 other cubes through its 6 faces, and each slice can only cut off one of those connections at a time, so you need at least 6 cuts. The fake fact is the first one. This is because circles are packed more densely like this, rather than like this. So even though the configuration on the right does look neater, it ends up not being optimal for large numbers of circles. Sometimes math is just a mess. Two truths and a lie, but with math. Can you spot the fake? First, if one Fibonacci number is divisible by another, then the same can be said for their indexes. Second, there are extra platonic solids in higher dimensions. Platonic solids are like the 3D version of regular polygons, and there are 5 of them. But in 4D, there are 6, and they're called regular 4 polytopes. Speaking of platonic solids, octahedrons can fill up space without there being gaps in between. That was all 3 facts, so it's time to lock in your guess. The second fact is true. To create a platonic solid, you must take several regular polygons, then fold them into the third dimension. There are 5 ways to do this, resulting in 5 platonic solids. Likewise, to create a regular 4 polytope, you must take several platonic solids, then somehow fold them into the 4th dimension, and there are 6 ways to do this. The fake fact was the third one. Here's why the first one is true, or at least the rough idea behind it. If you repeatedly split a Fibonacci number, you'll end up with the product of 2 Fibonacci sequences, one going up and the other going down. When they meet, 55 will be divisible by 5, as you can see here. The indexes will also meet in the middle at the same time, so 10 is divisible by 5. Full proof in the comments. Two truths and a lie, but with math. Can you spot the fake? First, this bell curve that you see everywhere is built from a formula that contains both pi and e. Second, it's well known that angles in a triangle add up to 180 degrees, but there's a similar rule for 3 dimensions. The angles in a tetrahedron add up to 360 degrees. There are 6 of these angles, one for each pair of faces. Third, there are an infinite number of primes that don't contain the digit 3 at all. That was all 3 facts, so it's time to lock in your guess. The first fact is true. Here's the formula. The reason E is here is because E has a lot to do with probability, especially when it comes to infinite possibilities. The reason pi is here is more surprising. It's because without this coefficient, the area under the curve would equal square root 2 pi. Don't ask me where the pi came from. Pi just shows up whenever it feels like it. But the area under the curve should add up to 1, since probabilities always add up to 100%, so this coefficient is needed. The fake fact was the second one. Just picture a really flat tetrahedron. The angles between these 3 faces are each almost 180 degrees, so the sum of these 3 angles alone is much more than 360. Two truths and a lie, but with math. Can you spot the fake? First, if you take a dodecahedron and extend the faces, the side length will increase by a factor of the golden ratio cubed. Second, this new shape is considered to only have 12 faces, similar to how a star is only considered to have 5 edges instead of 10. Third, this shape is often referred to as the forgotten platonic solid, as it is the only shape that fulfills all of the requirements except the concavity one. Now that you've seen all 3 facts, take a moment to think about which one you think is false. The first fact is true. This is because dodecahedrons are made of pentagons, which are very closely related to the golden ratio. The second fact is also true. It may seem counterintuitive, but faces can intersect each other to form a solid. Here, one of the faces is shown in yellow. The middle portion is blocked off by other faces. The fake fact turns out to be the third one. There are 3 other shapes that are also nearly platonic solids. All 4 are created by messing around with dodecahedrons and icosahedrons. Two truths and a lie, but with math. Can you spot the fake? Soap addition. Bubbles have some surprising connections to math because they naturally try to minimize surface area. First fact, these white lines, which we'll call bubble borders, always meet in groups of 4. Furthermore, when they meet, the 4 bubble borders are always equally spaced apart. Second fact, soap films, which are the surfaces of bubbles, always meet in groups of 3. It's a bit hard to see since they're invisible in this image, but you can visualize them coming together to form bubble borders. Again, when they meet, 3 soap films are always equally spaced apart. Third fact, you can make a custom bubble simply by twisting wires into any shape that you want, then dipping the whole thing in bubble solution. Pause here to think, then lock in your guess. The fake fact was the third one. This is because soap automatically tries to make the bubble as thick and strong as possible, so why would it spread itself thin by staying in the shape that you want it to be in? No, it'll make a weird shape like these. The incredible thing is a computer would take billions of calculations to find these optimal configurations, while soap just does it naturally.